Do you remember the 21st night of September? Love was changing the minds of pretenders while chasing the clouds away. Our hearts were ringing in the key that our souls were singing as we danced in the night. Remember how the stars saw the night away. Bania, say do you remember? Bania, dancing in September. Bania, it never was a cloudy day. Happy September 21st, everyone. Welcome to another Planetarium live stream. I am your host, Patrick Hess, the Planetarium Specialist at Union Station. If we get a copyright strike for that song, I'm going to go ahead and redo the intro. Welcome to another Planetarium live stream. My name is Patrick Hess, the Planetarium Specialist at Union Station. Thanks for tuning in. I hope you appreciated that silly intro. Welcome back. I hope you guys are having a good night. I know I am. You know, it's starting to cool down a little bit, but we're going to ring in the fall with just kind of a fun little deep dive today. Less deep, more of a shallow dive, I'd say, into seasons. We're going to talk a little bit about how the seasons change, which is kind of a simple topic on the surface, but there's some interesting things we can dive into all about seasons. And then since we're talking about seasons, I kind of abstracted a little bit and was like, oh, well, let's talk about time. And, you know, what does time mean and how does that relate to astronomy? So we're going to dive in a little bit there. Should be a lot of fun. But as we've been doing for a little while, I'm going to start with some news items. So we're gonna go over what happened over the past week. Also, I wanted to thank you guys for bearing with us last week, since last week's stream wasn't able to be live. Hope you guys enjoyed that and that was okay with me answering your questions in the comments section. But we are live officially, so don't forget, if you have any questions or comments, please go ahead and put those in the comment section and I'll try to answer those. And if you just have a shout out, want to say hi, then type that in there as well, and I will give you guys a shout out. So let's go ahead and start and see what we've missed in the news, some astronomy news today. And let's see. Okay, so this is kind of fun. The Voyager 1 space probe reached a milestone just the other day. It passed 14 billion miles away from the Earth. Pretty crazy. And this is kind of fun. The Jet Propulsion Laboratory site for NASA has a mission status tracker here, where you can actually see its distance in real time. And as you can tell, it's traveling pretty quickly, passing by dozens of miles in seconds. It's continuing to go pretty far out of the solar system. There's a lot of other information about the Voyager probe, and there are trackers for a lot of the other probes. And it even has an interactive little display here, which is really awesome. It shows the Voyager probe and its current configuration, and then you can even zoom way out here, and it's going to take a bit of strolling, continuing to zoom. There we go. So we can kind of get a feel for how far away the Voyager probe is relative to the planets. So you can see Pluto way over there, as well as some other probes like New Horizons, the Pioneer probe, and Voyager's sister probe, Voyager 2. So pretty cool, pretty exciting, and it's awesome that, you know, we are still communicating and gathering science from these probes that are really far away and were launched decades ago. So, you know, it just goes to show that, you know, these missions, although they have primary mission profiles where most of their science is going to be gathered, sometimes, if all goes well, we can continue to gather science from them years or even decades into the future. So pretty awesome there. Let's see. The other really big astronomy news announcement came with the publication of this paper here in the Nature Astronomy publication, which is that scientists have actually measured trace amounts of phosphine gas in the clouds of Venus. Now, this is significant because here on Earth, this particular type of gas is created by biological processes, life, basically. So here on Earth, that type of gas comes from life. Now, this is not proof that there's life on Venus, but this is an interesting marker and basically sort of a flag waving of, like, you know, probably a reason why we might want to check out Venus sometime in the future. And I believe there have been some interviews with some NASA scientists who have mentioned that they are starting to think about, a potential mission to Venus. There were a couple proposed back in February, a couple mission profiles that could be sort of activated or funded to develop probes to go to Venus. But these missions will take years, sometimes even decades to produce, because they got to build the probe, get all the science ready and all that. But pretty exciting that there might be reason to go back to Venus. For a while we haven't really thought about going back to Venus since the 70s. But if there could be life in the clouds of Venus, that could be a really exciting reason to go back. Another pretty cool and exciting news story popped up here from Australia. They actually launched their first private space rocket. This was after a scrub launch. Their backup launch occurred, and this rocket is not quite orbital class, so it couldn't get all the way to space, but it is space capable. And it's just exciting to see another country sort of get to that point where they could be launching orbital class rockets in the near future. And there are just 9 countries right now with orbital capable vehicles. That's Russia, the United States, France, Japan, China, India, Israel, Iran, and North Korea. So there could be a 10th sometime soon. It could be Australia. So congratulations to those scientists down under on that historic launch. Pretty exciting. Getting a couple shout outs. It looks like Betty's also welcoming autumn. Me too. Well, bring it on. We're gonna deal with it. It's been a weird year, but we'll make the best of it, right? Sherry's saying hello and giving a shout out to September 21st. Hope you enjoyed our introduction. And Tammy tuning in, one of our MVPs, our longtime watchers. Thanks for watching again, Tammy. Great to have you back here. And just as a reminder, we've been streaming live since since April of this year. This is actually our 40th live stream, which is super exciting. And as a reminder, you can rewatch any of our previous live streams on our YouTube channel. We've uploaded all of our previous streams there, and I've sorted them out by different topics we've covered. All of our deep dive streams are there. All of our live star tours are there back before we reopened to the public. And we've got a couple Q&A sessions that are pretty fun, where it's a lot of interacting with you guys. And if you enjoy the Q&A sessions, then be sure to leave a message in the comments, because we can always bring those back. We actually did a Q&A session just a couple weeks ago, earlier in September, and it was a lot of fun. And we've covered so many topics. We've covered Harry Potter astronomy, as well as other fictional universes from TVs and movies. We've talked about many planets in our solar system, taking deep dives into those. Yeah, a lot of really interesting topics. So I'd encourage you to go back and rewatch any of those if you'd like. And we've got fun topics planned for the rest of this year if we continue streaming, which if you're enjoying this, be sure to let us know, because we're enjoying it and we would love to keep bringing you these live streams. And just as one last reminder, Science City and the Planetarium are open to the public now. And if you feel comfortable joining us in person, we are open and you can buy tickets online. We've been having a lot of fun having guests back, and we've been doing everything we can to make sure everything is nice and safe for those guests who feel like joining us. But of course, if you do or don't, you're always welcome to keep tuning into these live streams. So remember to leave a comment or a question in the comment section, and I will try to answer them. But for now, looks like we just got a comment from Casey saying hello from Gladstone. Love these streams each week. Awesome. So glad to hear it, Casey. Thanks for tuning in. And Amber's watching from Nokesville, Virginia. Awesome. Very exciting. All right, so we are going to dive into our topic today, which is seasons and time. And we're going to start by talking about seasons. So, how do we define a season? Well, there are kind of 2 main ways you can think about seasons. You can think about them culturally or astronomically. Now, cultural seasons, they come in all varieties of shapes and sizes and lengths, just different ways to sort of divide the year up. There are some, for example, some South Asian calendars and Native American calendars actually who use a 6-season system. And traditional Chinese calendars actually has a calendar with 24 seasons. And if you'd like to learn more about that, you can check out our live stream that we did on June 15th, where I talked about a couple different sky cultures. We talked about Chinese sky cultures and Egyptian sky cultures, I believe. And then we did a whole stream about Native American sky cultures on a different day too. So you can check out that stream if you want to learn more about that. As far as the naming of seasons, one of the fun facts I like talking about is, there's obviously winter, spring, summer, and fall. And we divide these seasons up generally by some important and key dates, which I'll talk about once we get into the astronomy of science. But winter begins after the winter solstice, which is usually around December 21st, which is the shortest day of the year. And that's also called the hibernal solstice. The word hibernal is the adjective describing something in winter, which is kind of a lesser known one. Not a lot of people know. And then the spring begins after the spring or vernal equinox, which equinox means equal nighttime, basically referring to the fact that daytime and nighttime is the same length during that equinox, and that's when spring begins as the days get longer than the nights. And then the summer solstice, which is on June 21st, the beginning of summer, is the longest day of the year here in the northern hemisphere. We also call that the estival solstice. I just love that word. Estival refers to something in the summertime. It just sounds so fun and lively, like a festival. But estival is a great way to describe something summertime. And the one people mostly know is the fall or autumnal equinox, which is when fall begins, and that's today. So today is the autumnal equinox, September 21st, first day of fall, and today daytime and nighttime are the same length. Unfortunately, the bad news is that from this day forwards, all the way till December 21st, the nights will be longer than the days. But the great thing about winter starting is the days start to get longer at that point too. So give and take. Now, some scientists think about seasons differently. Like ecologists think of seasons. I think of the year as being divided into 6 seasons. There's a pre-vernal, which is when tree buds begin to appear. Then there's vernal season, then estival, and then the serotinal. I'm not sure exactly how to pronounce that, but serotinal, which refers to serotiny, which is when many seeds are released due to environmental triggers, seeds in plants, and this is when trees begin changing color, and traditionally that's the harvest season. Then there's the autumnal season and hibernal season. So sort of if you're thinking about ecology and nature, if we're dividing the year tied to things like floral and animal events like flowers blooming and hibernation of animals, then those scientists think of the year in 6 seasons. Depending on where you are, if you're in tropical regions, you might have 2 seasons. There's the wet season and the dry season, monsoon season and non-monsoon season. And then if you live in polar regions, there are 2 seasons, which is basically day and night. And we'll talk about why that is, why you might end up with a couple months of nighttime if you end up on one of the poles. So now we're going to be focusing mostly on astronomical seasons and talking a little bit about how our year changes and how time changes because of astronomy and because of how the Earth is positioned in relation to the sun mostly and other things in our solar system. Now there are some misconceptions I want to dispel, and some people might think that these are some just common sense things, but I try to not think of astronomy and science in that way. They always say there's no such thing as a stupid question, and that's really true, because for me, whenever somebody doesn't understand something, I just think of that in a positive light as sort of a jumping off point to learn more about what's really going on. So don't feel bad if you thought this, but a misconception, a common one, is that the seasons are caused by Earth's elliptical orbit. So the Earth's orbit is elliptical, which means it is not perfectly circular. So in this diagram here, the yellow line is the Earth's orbit, and then the red line would be a perfect circle here. And as you can see, Earth's orbit is slightly different. It's slightly offset. So for that reason, actually I got that backwards. So the red line is Earth's orbit, and then the yellow line would be a perfect circle. So a common misconception is that, oh, well, it's colder when the Earth is farther away from the sun, which on its surface could make sense. And again, it's okay if you think that, but unfortunately that is a misconception. And you can easily dispel this misconception just by looking at, well, if the Earth's orbit is elliptical, when is it furthest away from the sun and when should it be colder? Well, it's actually furthest away from the sun in the summertime, in June. And I just realized, hey, I was right the first time. So in this, I really should have kept the legend on this chart here. But so, okay, the yellow line is actually the Earth's orbit, and the red line is a perfect circle. So in June, in summertime in the northern hemisphere, the Earth is actually further away from the sun than it is in December in the wintertime. So for that reason, if it's warmer in the summertime when the Earth is further away, then the seasons are definitely not caused by the Earth's position relative to the sun. The Earth's perihelion, which is the scientific term for when the Earth is closest to the sun, is in January, actually. And the difference that the Earth makes as it does its elliptical orbit, there's only about a difference of 3 million miles, which is just about 3% of the Earth's distance from the sun. So that amount of distance could not really change the climate that much. So the real reason that seasons occur is because of the Earth's axial tilt. So here we are back in Space Engine, our 3D astronomy software, which is really cool. And this is going to hopefully help us to understand why the seasons are changing. So this is, actually, let's get to the present time here. So this is actually right now what the Earth looks like. And I've gone ahead and added some charts here, or some lines showing us the pole. So the North Pole is pointing up there. And then this line here is basically the equator. So it's showing sort of what the tilt is, because this software unfortunately can't put grids on the Earth. But you can see that's sort of the axis of the equator here. So you can see right now the Earth is tilted over to its side. Now the Earth's tilt is 23.5 degrees currently, which we'll talk about how that changes a little bit later. But the tilt of the Earth is what really causes the seasons. Now, right now, if I adjust things here, let's rotate around. So this, again, is the present configuration of the Earth and the Sun. So you can see there, the calendar is showing the current, there we go. Okay, yep, so the calendar is showing the current date and time, just so you guys can see that. Sometimes I forget that, I'm floating here in space. And so today is the equinox, remember? It is the autumnal equinox. And what that means is that right now, the Earth is configured in this way. So the the tilt of the Earth here, well, let's get, there we go. Tilt of the Earth here is sort of parallel with its orbital position. So basically, if you look here, look at the shadow on the North Pole. You can see the shadow between the daytime and nighttime crosses straight through where the North Pole is, okay? So remember that, because I'm going to adjust things here. And just to show you, so this is the current position, okay? So basically, since the Earth is its tilt is parallel with its orbital path, basically during today, throughout the entire day, as the Earth rotates around, no matter where you are on Earth, your daytime and nighttime is going to be basically the same length. Now let's fast forward here. So I'm going to go ahead and adjust the clock, and we're just going to go forwards 3 months. So we're just going to go to December 21st. And this is, remember, the winter solstice, or the hibernal solstice. And at this point, this is the start of winter here in the northern hemisphere. And if I angle this, so this is parallel with, so I'll just zoom way out here so you can see there is the Earth's orbit right there. And if I zoom back in here without crashing into the Earth, we're going to keep things lined up here. So we're kind of parallel with the plane of our solar system, which is called the ecliptic. Oh, I'm sorry. I just realized you guys couldn't see what I was doing. All right, let's do that again. I think I accidentally just pressed a button. Okay, so we're back in Space Engine. I'm not sure how much we saw, so I'm just going to backtrack a little bit. So this is the plane of the Earth's orbit. So there's the Earth's orbit around the sun. The reason it looks distorted and super elliptical because I have the I have things kind of zoomed out, so it's got a kind of a lens distortion. So that's why it looks kind of distorted there. So ignore that fact. We're just going to zoom back in here, back to the Earth, trying not to crash into it, keeping things lined up with the plane of our solar system. Oh, come on. All right. Whoa, there we go. There we go. Okay. So back at Earth. Oh. Okay. There we go. All right. I just realized the clouds are off too. Let's keep the clouds off so we can see the continents. All right. So this is winter. So this is the winter solstice. This is December 21st, which is the shortest day of the year in the northern hemisphere. And as you can see now, look at the North Pole. We've got a lot more of the North Pole in shadow. And it's not lined up, so the shadow is not lined up there. And what's going to happen now is, if we were to fast forward time here, you can see that a point in North America will spend a lot less time in daytime. Remember, that is the shortest day of the year, the longest night of the year. And also, you'll notice that if you were at the North Pole here in on the winter solstice, no matter what time of the day it is, you'll always be in nighttime. So that is why, if you get far enough north, you'll actually experience perpetual daytime and nighttime depending on the season. So now what I want to do is we're going to fast forward another couple months. We're going to go to 2021, and we're going to go to 321, which will be the vernal equinox, the start of spring. And so we can see that the Earth's pole is now aligned again with the axis, and this time all the continents are sort of facing the sun equally in this configuration. And then if we fast forward again to summertime, so we'll just go to 6:22 or 21, where the time is kind of marching forward, so, but that's okay, it's still close. So now you can see that the North Pole is kind of pointing towards the sun at this point. And if you're north of the equator, you are going to experience a longer daytime. So any point north of there is going to spend longer in the daytime, as you can see here. So yeah, so if you line up from the North Pole, you can see that there's more of the northern hemisphere exposed to daytime than nighttime, and that's why the days are longer in summertime. But, you know, this is all going to be reversed if you're in the southern hemisphere, and that's why if you are, say, in Australia right now, you're probably pretty excited because spring just started, and things are going to start to warm up a little bit. So, so in that way, you know, the seasons are not universal even here on Earth. If you basically, they're just reversed if you're in the southern hemisphere. Now, if you look at a map of the Earth, a lot of the landmass in the southern hemisphere is further north than the landmass in the northern hemisphere is south. That makes sense. Sort of most of the landmass on the Earth is kind of shifted upwards. So you don't hear a lot about sort of really cold, snowy winters down in the southern hemisphere in the middle of June. But there are some places, if you get far enough south, that you might experience that. But, you know, there are other things that change climate too, like weather patterns and you know, the atmosphere. So, but that is a little diagram, a little demo of hopefully helping you to understand a little bit of how the seasons are working. Just a nice way to visualize that. There is another way we can visualize it that I like using, and that is going to use Stellarium. So we're going to go back over here. This is free software you can download that will just give you a view of the night sky. It's sort of like a virtual planetarium. Now, normally we've got our Kansas City backdrop, but I am actually going to change that just so we can see the southern horizon here a little bit better. Keep clicking the wrong button. There we go. So we're just going to go to this open field landscape here. I want to show you this. So another way we can visualize the changing seasons is in the position of the sun. So if I rewind time to noon here, we will see the sun is at a point in the sky that is not too high and not too low. If I put the azimuth grid on, which is basically just showing us the sort of a grid above the horizon, we can see that today the sun will be, let's see, 10, 20, 30, 40, about 50 degrees here, right around noon. Now, depending on the time of the year, the sun's position will change, and there's actually a really cool script that's in here that we can see something. Now, this is called the analemma, and this is going to show us, if it loads, oh, okay, it brought the, oh, this is kind of awkward. I don't know why it brought the backdrop back again, but that's okay. I'll show you in a second. So, so this is going to show us basically, it's recording the sun's position throughout the year. So it might be hard to see on the stream, but you can see the weeks going by here, and it's basically showing the sun's position all 52 weeks of the year. And once it lets me get control again, I'll be able to show you a little more clearly, because this is so helpfully. Whoop! Oh, well, shoot. let's try that again with the original backdrop. And hopefully it'll let me do that. If not, then that's okay. I'll just explain it anyway. This didn't happen when I tested it earlier, if you can believe it. Okay, well. So basically what we're seeing here is we are sort of taking a picture of the sun at noon every day of the year, and we're plotting that out on a graph of the sky. And what we see here is a shape called an analemma. And so the sun is actually making a bit of a figure eight. Now, first of all, notice how in the summertime, the sun is going to be very high in the sky. There's the summer solstice. In the winter, it's going to be lower in the sky. The winter solstice is the bottom of this diagram here. And then the equinoxes are where that diagram crosses over. Now, this figure eight is caused by Earth's elliptical orbit. This diagram here. There we go. So because of Kepler's second law of planetary motion, Kepler was a physicist way back in the day, and he devised some physics laws that described how things moved around in space. Basically, if you are an object orbiting an elliptical path, then when you are close to that your parent object, you'll move more quickly than when you're further away. So basically, when the Earth gets close to the sun, closer, relatively speaking, in its elliptical orbit, it will actually speed up a little bit. And that is why that figure eight pattern happens in the analemma there. Because at certain points of the year, during the solstices, the Earth will be moving at a different speed. It won't always be moving at the exact same speed going around the sun. Kind of interesting there. Another interesting thing is because of this changing in its speed, solar noon, which is the point at which the sun is highest in the sky, will actually vary by as much as 16 minutes. So 12 o'clock noon is not always when the sun is highest in the sky. Today, 12 o'clock noon would be when the sun is highest in the sky, but in the summer and fall, it'll vary by about 16 minutes on either side. Before I move on, I'm going to check in, see, we've got a couple of people who've commented. Genevieve says, enjoying live streams very much. Oh, well, thanks. I'm enjoying you watching, Genevieve. Don is tuning in. Hi, Don. Glad you're watching from Corpus Christi. And she says, keep being brilliant. I will do my best. And Kathy says, Kansas City, home of the Chiefs. Heck yes. This is Coca-Cola, by the way. To all of those families watching at home. All right, now one thing I wanted to talk about a little bit is other solar system objects. You know, you might ask, do other planets in our solar system have seasons? And let's check here. Oh, there were a couple things I wanted to mention before I just glossed over in my PowerPoint. So I talked about how the Earth reaches perihelion when it's closest to the sun in January. And here's just a chart showing us here in Kansas City the day of each year of the next 4 years when the sun will be closest, or sorry, the Earth will be closest to the sun, or the sun will be closest to the Earth. I guess that's true. So if you're curious, it's all usually around the same time of the year there, with some small variations. And also, here's a cool picture just showing you that size difference. So these are just photos of the sun from the same angular diameter showing its relative size. So it's really not, it's not that we get that much closer or farther away from it. And the sun is very, very bright and hot, so it's really not changing the amount of radiation reaching us. So here's a chart that ended up a lot blurrier than I thought it would, but this is just showing us seasonal shifts on other planets. So this is telling us things like the length of the day, axial tilt. I do have a better diagram though showing that. That shows us the axial tilt a little better. So just to kind of run through the planets in our solar system really quickly, Mercury has one of the most elliptical orbits in our solar system, and so it has some pretty measurable seasonal changes in temperature, but because it doesn't have an atmosphere, these temperature changes happen so drastically that every day and night cycle the temperature changes by almost 1,000 degrees Fahrenheit. So it'll be 800 degrees in the daytime, but then minus 200 in the nighttime. So that kind of changes or muddies the data when it comes to measuring seasonal shifts on Mercury. As for Venus, it has a very small axial tilt of about 3 degrees, although it's actually orbiting in an opposite direction. In this case, the diagram is just showing us that it's sort of upside down, which is not an incorrect way to think about it. But since Venus has such a dense atmosphere, there really is not much variation in combining the fact that it has a dense atmosphere and it has a very, very small axial tilt, there's pretty much no measurable seasons on Venus. It's just always hot. It's 900 degrees in both the daytime and nighttime just because of that thick atmosphere. Mars has a similar elliptical orbit to the Earth and a similar tilt to the Earth. You can see there it's about 25 degrees. And since it has an extremely thin atmosphere, it experiences seasons, but in an extremely exaggerated way. So there are extreme summers and extreme winters on Mars, barely any fall and springtime. Although I gotta say, having lived in the Midwest for about 30 years, it kind of feels like we're on Mars sometimes, because we usually get a couple weeks of fall, and then bam, suddenly it's winter. But let's hope that we get a bit of a longer fall this year. That would be greatly appreciated, Mother Nature. As for any of the outer planets, all of them are so far away from the sun that they really don't experience any noticeable changes in weather, even though some of them are tilted to a pretty extreme degree. There are some things that do change the climates on other, not really planets, but a lot of moons. There are tidal gravitational forces that will tear at moons as they change their positioning in their orbits, and as they move past other moons that also pull on them. If you want to learn more about how those tidal forces affect some of the moons in our solar system, I'd encourage you to watch last week's live stream, which wasn't live, last week's pre-recorded stream, in which I counted down my top 10 favorite moons, and there were a couple moons on there that were pretty interesting when it came to climate. So you can check that out. That was the one that was published on September 14th. So if you want to check that out, you can. And there are a couple fictional planets. One of the best examples is the planet that the Game of Thrones series takes place on. Those seasons last for years at a time, which seems fictional, but there are some potential systems that could exist in the real universe that could create a planet with sort of unpredictable seasons like that. If you want to learn more about that, I would encourage you to watch the Fantastical Universes of Fiction live stream, which would be the May 20th live stream, where we dived into a couple different fictional universes and how their astronomy works. And we talked about weather in Westeros. So check that out for sure if you're curious. All right, before I move on, let's jump in and see. It looks like we got a question from Eric. Eric asks, how will the Earth's wobble around its axis impact the seasons? Ooh, that's a great question. And that actually leads us straight into the next section. You read my mind, because I am going to talk a little bit about some other things that affect seasons on Earth, and specifically things that affect time on Earth, because seasons exist because of the Earth's relationship to the sun and the time it takes to go around the sun. There are a couple irregularities that might affect this. And so we're going to pivot a little bit, and I'm going to start, let's kind of talk a little bit more about just time in general, how we measure time and how we measure seasons and things like that. Before clocks, we measured time in a couple different ways. We used observable physical processes like the rising of stars. For example, the first appearance of Sirius was often used to mark the flooding of the Nile each year. There's also, of course, the angle of the sun, using pretty simple tools, measuring the angle that can help you figure out what the seasons are. And then, of course, the lengths of shadows being cast, things like sundials, of course. As for today, how do we measure time today? Well, since 1967, one second has been defined as exactly this: the duration of 9,192,631,770 cycles of the radiation corresponding to the transition between two hyperfine levels of the ground state of the cesium-133 atom. Whew, that's a mouthful. But basically, this is the atomic clock. So this is just a measurable oscillation of an atomic state, essentially, that is, we've just decided, essentially, is exactly 1 second, and just works well with how we measure the year and things like that. We also call this universal time. Now, the international standard is what we call Coordinated Universal Time, or UTC. The initials are switched around because of translation. So UTC is our human-defined time, basically. And that doesn't always correspond with universal time, which we'll talk about. Now, let's talk about some irregularities. As a lot of people know, the Earth does not take exactly 365 days to go around the sun. It actually takes exactly, close to 365.2422 days to go around the sun. And this is why we have leap years. So a leap year occurs in a regular interval And basically, during a leap year, we would add a leap day, which is February 29th. Now, a leap year is not every 4 years. A lot of people don't realize this, but because the year is this sort of non-standard amount of time, again, 365.2422 days, we have some special rules about leap years. So basically, the way this works is that a leap year is only on a year that's divisible by 4, so every 4 years, but every 100 years we skip a leap year, unless the year is divisible by 400. So basically, we have a leap year for every year that's divisible by 4, but on the turn of centuries, it'll change. So, for example, 1700, 1800, and 1900 were not leap years, but the year 1600 and the year 2000 were leap years. So you can see in this chart here, this is just showing us leap years over the past few centuries. And as you can see, the year 2000 was a leap year, but all those other ones were not. So basically, if you do the math, that fraction ends up as 365.2425. So really close. And we're going to call that close enough for, I think it probably will keep us sort of in sync with the seasonal shifts of the Earth for a couple thousand years. Now, the modern Gregorian calendar, in which we use leap years, was adopted in the 1500s, and for us, it was adopted by Britain and its colonies in 1752. It's kind of a funny story if you look up some news articles from back in that day, because since they were on the Julian calendar, which was a little bit off from that, they actually had to skip September 3rd through September 13th to catch up with other countries. So if you were born in 1752, on one of those days, well, you couldn't have been born on one of those days, because basically the calendar went from September 2nd to September 14th. So kind of if you ever want to pick a fictional birthday for somebody as a trivia thing, I don't know, then you could pick September 11th or September 10th or 9th or something like that in those dates. So kind of funny. 1752, if you were a member of Great Britain or one of its colonies, there was no September 3rd, 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th, or 13th. So there you go. Now, as for Eric's question about Earth's wobble, that is another irregularity which we have to account for. Now, we call, so the Earth has precession, where it sort of goes around in a circle, but it also, there's an extra wobble that I've not mentioned before called nutation, which is basically the changing of Earth's rotational axis. So it's kind of like, it's sort of nodding. So even as the Earth precesses around its axis, it doesn't stay at 23.5 degrees. This is a diagram showing us that nutation. Again, that's N-U-T-A-T-I-O-N. And this is caused from tidal forces between the sun and the moon, as well as actually some measurable deformations in the Earth's crust, changing basically the physical properties of Earth as a rotating object. But so basically, the Earth, the North Pole will move around every 24,000 years in precession, but also every few thousand years, the Earth will also sort of tilt. So right now, it's at 23.5 degrees, but as you can see, it is sort of lessening in its tilt right now, and it will kind of oscillate back. And this oscillation is also not uniform. That oscillation will change quite a bit due to all those other processes. And this will change. This will affect things like the length of the day. Now, another thing that affects, and this is kind of fun. This is a photograph in Mexico, I believe, or somewhere in Central America. This is basically the Tropic of Cancer, which is one of the geographic lines that changes year to year. So this is actually, they put signs up basically as the Earth's tilt changes. And it changes not a bunch, just a couple yards, as you can see, but it is measurable and visible to the human eye. So kind of crazy that you can actually, visit this spot and see how the Earth's axial tilt is changing. Belle is tuning in from Asheville, North Carolina. Thanks for watching, Belle. Glad you're joining us. All right, so hopefully that answers Eric's question. Now another thing about the Earth is that its rotational velocity is actually slowing down. I think I mentioned this a couple streams ago, but back when the Earth formed, the day used to be 6 hours long. So it only took 6 hours for the Earth to spin around. But over billions of years, the Earth has slowed down because of, again, tidal forces from the moon. The moon is essentially just pulling on the Earth, kind of arresting its rotation. And even during the time of the dinosaurs, the day was about 21 to 22 hours long. So today it's 24 hours long, but over the course of millions of years, it will continue to get slower and slower. I'm not sure if it'll ever get slow enough where it'll just sort of stop and become tidally locked to the moon, or if by then our solar system will have ended when the sun expires. I'll have to check the math on that. That could be a fun thing to find out. But so that affects the length of the day. And there are even some sort of human scale events that can affect the length of the day. For example, in 2004, there was an earthquake in the Indian Ocean that caused the day to measurably shorten. That year, the day was 3 microseconds shorter because the earthquake actually adjusting the distribution of mass on Earth, changing the Earth's moment of inertia. There's also this thing called post-glacial rebound, which is we're actually in the middle of, ongoing since the last ice age. Just as things are melting naturally, that changes the distribution of Earth's mass as well, which affects the length of the day. This is actually the same principle as ice skaters. So when an ice skater tucks their limbs inside, they'll spin up. That's called the moment of inertia. So this is showing us just a chart over the past few decades, looking at basically the deviation of the length of a second, so how the Earth's rotational period is changing. Now, to counteract this, we needed to do something because given enough time, even with leap years, our time system is going to be off, and we need to make sure it matches up, especially when we started sending more probes and rockets and satellites into space that are it's really important to keep them aligned with the Earth and with the position of the Earth as it rotates. So what scientists did in 1972 to account for these irregularities in its rotational velocity, they introduced something called a leap second. Leap seconds are different than leap years. They are not scheduled, so they are just determined by humans, which is kind of crazy. There's an organization called the International Earth Rotation and Reference System Service, or IERS for short, that decide on when a leap second is going to take place, and they've been doing that since 1972. There have been 27 leap seconds introduced since then. Last one was in 2016, and I just checked. There are no future ones announced. They announce these every 6 months because you want to let the world know if there's going to be an extra second added to the clock, because especially if you're a system administrator or a computer programmer, that extra second could really mess up computer systems. Generally, they add a leap second when the difference between UTC and universal time, again, I mentioned that's the human clock and that official atomic clock, if that difference gets close to 0.6 seconds, that's usually when they schedule a leap second. So again, the last one was in 2016. I don't know. I remember that. It was a big news story. They usually do it at the end of the year or in the middle of the year in June. I think that one was in December. Actually, you can see the leap seconds on here plotted out. That's what these red dots are. Yeah, and this one was at on New Year's Eve, I believe. Basically, there was a 1 minute that had 61 seconds in it, which was kind of weird to see. I think I was even like looking at my clock, watching that happen, and I could actually see it, which is pretty weird. But just kind of a weird thing about living on this planet. A lot of people think all these processes are very standard and things aren't changing, but they are changing a lot in measurable ways. There's one more thing I wanted to dive into, although we did get a question from Carrie, who asks, does the Tropic of Cancer move because of the Earth's wobble? So the Tropic of Cancer, just to specify that, let's go back to that picture. So the Tropic of Cancer here, we'll just let me load up this picture. Ooh, let's see that zoomed out a little bit. So this is let's see, how do I want to define this for you all? So basically, this point here is it is basically the furthest north place on the Earth where the sun can be directly overhead. And this occurs in the summer solstice or the estival solstice. So this will change again as the axial tilt shifts, as we saw in this diagram right here. So Carrie, yes, the Tropic of Cancer does change because of the Earth's sort of nodding wobble. Now, the Earth does a lot of wobbling. It wobbles around, the North Pole wobbles around like a top spinning, but it also wobbles in that way. And you could say it wobbles in its orbit as it kind of gets closer and further from the sun. The Earth is just kind of wobbly, really, I guess. But hopefully that answers your question. So yeah, the Tropic of Cancer is not fixed. It's constantly changing. And that picture, by the way, I just checked. That is in Mexico. Mexico Highway 83, it looks like. So if you want to visit there, you can check that out. All right, so the last little thing I wanted to touch on was relativity, because time also will change depending on your position and specifically how fast you're moving. Now, scientists back in the day, Galileo, Newton, and most other people in the up until the 20th century, they thought that time was experienced the same for everyone, everywhere, no matter where you were in space, on Earth, anything like that. But today, our modern understanding of time is different. It's based on Einstein's theory of relativity. And we're not going to dive too deeply into that, but basically we know that time is experienced differently depending on your relative velocity. So essentially, if you start traveling faster than somebody who's standing still, then you will experience time more slowly than that other person at rest outside of your reference point. Now this is maybe pretty hard to comprehend. I know sometimes I have to stop and pause and really think about this too, but all this to say that I wanted to bring this back up. We can actually observe this here on Earth. So just as a specific example, an astronaut who is aboard the International Space Station is traveling very quickly, orbiting the Earth, and they actually will not age as much as somebody back on Earth. So we actually, this is sort of an important, well, it's a very small amount. You know, we're talking about microseconds here. But basically, if you're in space traveling that quickly, then you will be slightly younger than somebody who was born at the same moment as you back on Earth. Another example is GPS satellites. Satellites that orbit the Earth are moving really rapidly relative to fixed points on the Earth. And GPS satellites are all about fixed points on the Earth because they're used to triangulate fixed points on the Earth. And so they have to account for relativity. They have to account for the change in basically how the satellites are experiencing speed relative to people back on Earth. Because when you're calculating positions of things like that, from something so far away, even a tiny difference could make a tiny number difference could make a big difference when you're talking about the position on something on Earth. Here's a diagram that kind of shows that relativity as well. So imagine the red clock here is an astronaut orbiting the Earth, and the blue clock is somebody on Earth. So you can see this is exaggerated, of course, but basically, since this red clock is moving more quickly than the blue clock, or relative to it, then its clock is moving more slowly. This can also could also be experienced if anyone were ever to fall into a black hole. So let's go over to Sagittarius A star, the black hole at the center of our galaxy. And if you were to ever start falling into a black hole, it would be an unpleasant experience. But if you were to watch somebody falling into a black hole, it would be a very weird experience, because what you would see is you would see that rocket ship traveling towards the black hole, but as it got closer, it would look like it's slowing down. Now, if you were on the rocket ship, looking outwards, it would look like everything else in the universe was speeding up. So basically, as you're falling towards a black hole, you are accelerating, sometimes close to the speed of light. And as you're accelerating, you will experience time dilation, which basically means time for you will be moving more slowly than time elsewhere. And so people, if you watched a rocket ship falling into a black hole, you would never see it fall into the black hole, because that rocket ship would appear to just slow down so much because its speed relative to you is accelerating so much. It's, again, a really crazy concept. If you want to learn more about the specific science behind that, I dive much more in depth in my live stream about Hollywood astronomy, where we talked about Interstellar, a Christopher Nolan movie that was on July 20th. So watch that if you want to learn more about relativity, because that is a bit more of a complicated topic that unfortunately we don't have time to dive into, because we are already brought to the end of our live stream today. So yeah, that was a bit of a rambly journey, since we covered a lot of different things, from seasonal shifts to how we experience time. But hopefully you saw a through line there. I just figured today, being a special day, of the year in our calendar. A lot of people are probably wondering, why is that important? Yeah, so anyway, hope you enjoyed that stream. There's one more question from Eric asking about a background noise you might have heard. There's a special guest that might join us for the end of our live stream, so let's see if she will join us. Hey, baby. Okay. Here. So, there's a new friend. Ooh, uh-oh. Who's a little bit skittish. Yeah. This is Phoebe, a new feathered friend who might be joining us for a future live stream. But Phoebe, why don't you go ahead and sign us off for this live stream? Thank you all for coming and for watching another Planetarium live stream. Hope you enjoyed it. Next week, we are going to be talking about TV astronomy. I've done a live stream about movies, but there's a lot of really cool TV shows that talk about or involve astronomy or take place in space. So we're going to dive into that. I'm sure Star Trek will make an appearance. So if you're interested in that and want to learn a little more about the science of television shows and how they relate to astronomy, then we'll do it then. So hope you enjoyed the stream, and Phoebe will hopefully see you for another live stream in the future, but I'll definitely see you next week for our next live stream. Again, I've been your planetarium specialist, Patrick Hess. Thanks for watching. Hope you guys have a great rest of your week, and we'll see you next time. Hey, bye, Phoebe. Yeah.